Okay, hello and welcome back to another video. So today I'm going to be deriving differential equations for how water and air temperature and molar concentration of water vary through a countercurrent cooling tower. And to do this, I'm going to be using the Lewis relation along with energy and mass balances. So to start, let's draw the cooling tower. So let's draw the tower. Okay, so we have water coming in, and let's say this is 60 degrees Celsius. Then we have water coming out. We can say this is at 30 degrees Celsius because it's water cooling, so the water coming out should be colder than the water coming in. And then we have air and then the water and the air are in two different directions. That gives you the counter current cooling tower. And then inside the cooling tower, there's going to be packing. And this maximizes the surface area between the water and the air for better heat transfer. So we're trying to find the change in temperature of the water with respect to position, the change in temperature of the air with respect to position, and the change in concentration with respect to position. So that's what we're trying to find. So looking at the packing, this is going to be represented by A, and it's going to be in units of meters squared per meters cubed, which is just meters. So if we look closer at packing, we have water coming in, water coming out, and then air is going to be in the opposite direction. And then this is as like the position is going to be in the positive direction. This is dz. So then for the liquid, going through the packing, we're going to have the liquid flow rate, which is going to be in the units of kilograms per meter squared times seconds. This is for the water flowing through the packing. And then for the air, we're going to have the superficial velocity, which is going to be meters squared per second times meters cubed. So first, remember we said we wanted to solve for the change in the temperature of water with respect to position. So to do this, we're going to look first at the change in thermal energy. And so we're going to have the liquid flow rate times the heat capacity times the area times the change in the temperature of the water. This is going to be equal to, first we're going to start with the heat transfer. So this is going to be the packing times the area, which is like the volume, times the change in temperature. So the temperature of the water minus the temperature of the air, times the change in position. We're going to add this to the mass transfer equation. And so we said before that we need the enthalpy of vaporization. That was in the last video. We're going to multiply that by the packing times the area, which is the volume. And then we're going to multiply that by the mass transfer coefficient times the concentration of water minus the concentration of air times dz. And then this concentration of air is really the concentration I'll just say it's the water vapor in the air. And then we can also note that I'll move this over first. Okay. We can also note that the concentration of water is going to be, that concentration is going to be pressure over the gas constant times temperature. And because this is the concentration of water, this is going to be the saturated pressure that we can solve for using Antoine's equation. So now we can simplify this where the areas cancel. And then we also want to get this term here where it's all equal to the change in the temperature of the water over or with respect to position. So we're going to get the change in temperature of the water with respect to position is going to be equal to the packing divided by the liquid flow rate times the heat capacity times the temperature of the water minus the temperature of the air. And then we divided by the dz to get that on the other side. It's still going to be plus the enthalpy of vaporization times packing times the mass transfer coefficient divided by the liquid flow rate times the heat capacity times, we said the concentration of water is the saturated pressure over the gas constant times temperature minus the concentration of air, or the water vapor in the air. Then I forgot, this should also be multiplied. I'll move this over. This should also be multiplied by the heat transfer coefficient, because that was the heat transfer equation. But there's the simplified equation to solve for the change in temperature with respect to position, or the change in temperature of the water with respect to position. So now looking at the air, we said that the volumetric flow rate of air was G, which was in meters cubed per second times meters squared. So we're going to have the change in the volumetric flow rate of air times the area times the concentration. Sorry, let me move this over, because this was to solve for the change in concentration with respect to position. So I'll just note that. Okay, and this will be equal to the mass transfer coefficient times the packing times the area times the concentration of the water minus the concentration of air, which we said was the saturated pressure over the gas constant times temperature minus the concentration of air, and this is going to be times dz. So then, like before, we want to solve for change in concentration with respect to position. We can cancel out these areas because to assume that they're going to be the same, and then we're going to be left with the mass transfer coefficient times the packing over the volumetric flow rate of the air times the saturated pressure over ideal gas constant times temperature minus the concentration of the air. And then finally, we want to solve for the change in temperature of air with respect to position. So this is going to be the change in the volumetric flow rate of air times the area, and this is going to be times the temperature of air times the heat capacity of air plus the enthalpy of vaporization over the density times the concentration of air. And then, to make sure that the units are the same, we have to multiply this by density. So we get a density at the beginning as well. And then this is still going to be equal to the mass transfer, which we said was the packing times the area times the heat transfer coefficient times the change in temperatures, the temperature of water minus the temperature of air, plus the mass transfer section, which we said was, let me multiply this by dz. And then the mass transfer section is going to be the mass transfer coefficient times the area times the packing times lambda, which is the enthalpy of vaporization, times the change in concentration. So the water was going to be the saturated pressure over the gas constant times temperature minus the concentration of air times dz. I'll put that down here. Okay. Here's our full equation. Now let's simplify and get it into these terms. So to start, looking at the left side of the equation, we're going to have the density times the volumetric flow rate times the area times the heat capacity of air times the change in the temperature of air, plus when we distribute the density over, it cancels because there's density in the denominator. So it's going to be the volumetric flow rate of air times the area times the enthalpy of vaporization times the change in concentration of air. And we know that the concentration changes because we just solved for it up here. And then the right side will all stay the same. So we're going to have the packing times the area times the heat transfer coefficient times the temperature of water minus the temperature of air times dz plus the mass transfer coefficient times the area times packing times the enthalpy of vaporization times the saturated pressure of the water over the gas constant times temperature minus the concentration of water vapor in the air times dz. So then the areas will cancel. There's that, and this can be rewritten. So this is going to be the density times the volumetric flow rate times the heat capacity of air times the change in temperature of the air plus volumetric flow rate of air times the enthalpy of vaporization times, or actually I'm going to just put the dz on the other side. This would be dz. That way when this dc change in concentration of air with respect to position, we already solved that up here. So this is going to be times the mass transfer coefficient times the packing over the volumetric flow rate of air times the saturated pressure over the gas constant times temperature minus the concentration of air. That's going to be equal to, this right side will stay the same. It'll be packing times heat transfer coefficient times the temperature of water minus temperature of air plus the mass transfer coefficient times the enthalpy of vaporization times packing times the saturated pressure of the water over the gas constant times temperature minus the concentration of air. And then this can be simplified further. So this volumetric flow rate of air will cancel. And then when we subtract this to the other side, this whole term and this whole term will cancel. So we're going to be left with the change in temperature of the air with respect to position is going to be equal to the packing times the heat transfer constant times temperature of the water minus temperature of the air divided by the density times the volumetric flow rate of air times the heat capacity of air. So here are all the equations that we just derived, and now we're going to go solve this in Excel. Okay, so now that we're in Excel, let's put in some of the variables. So we have the temperature of air going in is at 30 degrees Celsius. And then we have the temperature of water going in, which is 50 degrees Celsius. And then the temperature of water going out is also 50 degrees Celsius. So then we want this to be in Kelvin. 273.5, okay. And then same with the water. Oops. Okay. And then this is going to be the same. Okay. And then we need that the liquid flow rate is going to be 10. We have the G was the volumetric flow rate of air. It's going to be 5. And then the packing is 100. We're also given that the heat transfer coefficient is 50. And then the relative humidity is going to be 10%. Okay, so I just plugged in the information for the Antoine equation, and we also need the density of air, so we can say rho air, and this is going to be equal to the saturated pressure times the molar mass of air divided by the ideal gas constant times the temperature of the air in. Okay? We also need the mass transfer coefficient, the heat capacity of air, and the heat capacity of water. Heat capacity of air is going to be 1,000, and the heat capacity of water is going to be 4185. And then to solve for the mass transfer coefficient, we need to remember the equation from earlier. I'll write it down down here. We said that the heat transfer coefficient was equal to the density times the heat capacity of air times the mass transfer coefficient. So then if we're trying to solve for mass transfer coefficient, it's going to be equal to the heat transfer coefficient divided by the density, which is, I'll put in parentheses, rho air times the heat capacity of air. Okay, maybe. Not sure why this is not working. Let me make sure that these are named. There we go. Okay, so that's our mass transfer coefficient. Okay. And then we still need the saturated concentration, which is going to be, I'm going to solve it by using the Antoine equation. And then we want to divide it by the ideal gas constant times the temperature of the water going in. And then we want this to be equal to the temperature of the water. Oops. Ouch. Okay. Sorry, this was still the temperature of the water, and it'll be the same number because it's the same, but just so. Okay, here we go. And then I forgot here also need to subtract the 2. Okay, that looks better. And then now we just need the concentration of air going in, which is going to be equal to the saturated concentration times the relative humidity. Make sure all these are named again. Okay, so I missed some parentheses here, but I fixed it, and this is the equation that we're going to use for the saturated concentration, and then, oops. And then, again, this is the same, but with the new value that we got here, this is the new concentration of air coming in. And then we still need the change in position. We can say is 0.01, and in the height. Okay, so now we need to make a counter. Okay, so for the counter, it's going to start at 0. We need series in the column, and we're going to have it go until 1,000. Okay, here we're going to have Z. It's going to be equal to the counter times dz. Make sure all these have a name. Okay, and then we need concentration, T water, T air. Let me fill this down, okay? So this is going to be concentration of air in. This is going to be T water out. And then this is going to be T air in. Okay. And then we need E sat water. So this is going to be the Antoine equation. But this will be TW. Ooh, not that one. Okay, so I retyped up the Antoine equation. I think initially it was an issue with the parentheses here, but also this temperature of water coming out is going to be the same temperature as the air coming in. So I changed that as well, so that changed this column and this one. So now we need the concentration difference, the change in the temperature of water, change in temperature of air, and change in concentration of air. This is going to be equal to, we said it was the saturated pressure over the gas constant times temperature. So this is going to be saturated pressure divided by R times this temperature of water minus the concentration of air. What did it say? Oh, missed the parentheses. Okay, cool. So now for the temperature difference of the water, we are going to use the equation that we had from earlier. So this is going to be equal to, we have the packing, I'll put this all in parentheses, packing times the heat transfer coefficient times the temperature of the water minus the temperature of the air divided by the density times the volumetric flow rate times the heat capacity of air. Okay. Sorry, I was looking at the T air. I was looking at the wrong equation from earlier. So we still need, I'll just redo it. Okay, so that was for the change in temperature of the air. For the change in temperature of the water, it's going to be equal to the packing times the heat transfer coefficient times temperature of the water minus temperature of the air divided by the liquid flow rate times the times the heat capacity of the water. Okay, and this is going to be added to lambda. Okay, times the packing times the thermal coefficient oops, times this difference in concentration. Okay. Oh no. Okay. There. Okay. And then this should all be divided by the liquid flow rate times the heat capacity water. Okay. Okay. Sorry, also up here I said this variable wrong. This is the mass transfer coefficient. So now for the change in concentration, that equation was the mass transfer coefficient times the packing times the, not that one, times the concentration difference is going to all be divided by the volumetric flow rate. Okay. Okay, and now we're going to be using Euler's equation. It's going to be equal to where you are plus dz times the change. Okay. Okay, and then same thing. It's going to be equal to where you are plus dz times the differential. And then for air, same thing. Oops, where you are plus dz times the differential. Okay, all these, we can bring those all down. Okay, and then this, let me note, this is the bottom of the cooling tower. So now let's extend all these down. I'll just scroll to the bottom. Okay, and so this is what it looks like at the top of the cooling tower. And these are the values that we have. So at the top of the cooling tower, this is the Z value, which was 10. So we can go back up and calculate the height. So we said that Z goes all the way up to 10, so here the height is equal to 10. So then we want to optimize this. So we have temperature of water going in. This is going to be, I'll say, oops, I calculated. It's going to be equal to, the temperature of water is an I, so it's going to be I 1002. Okay. So now since we want to minimize it, we want to do the sum squared. So we want it to be equal to what we actually have, which is the temperature of the water going in. So TWN minus, or let me put that in parentheses, TWN minus what we actually got squared. Now we want to solve this using solver. So we're going to go to data, solver. We want to minimize this sum squared value by changing the temperature of the water coming out. So let's see it solve. Okay. So we have the temperature of the water coming out should be about 301 Kelvin, and the temperature of the water coming in is about 322 Kelvin. And then this was also, let me scroll back down so we can see. Yeah, so that's what it looks like for the relative humidity at 10%. So then we can change this to be at 5%. Let me change this back to 303.15. Okay, this was the original one that we had from before. Yeah, that's the original values. So this time we're going to do it, but we're going to have the relative humidity be 50%. Okay, and then this is still the same, this is still the same. So now we're going to use solver again. Let's minimize, TW out, and solve. Okay, and this time the temperature of the water coming out is at 304 degrees Kelvin, and the temperature of the water coming in is at 323 degrees Kelvin. So it's higher than when the relative humidity was at 10%.